Remember that as we talked about when we do balanced equations, the only thing that we change are the coefficients in front of everybody. If I knew the alphabet, that would be good. There we go. So again, only change these numbers. We never change any of the subscripts. We never add any numbers in between letters or symbols or anything like that. There's a couple of approaches, but again, most people sort of take a trial by error sort of approach, put some numbers down. I personally, as I mentioned, like to do a table as we did, and it kind of just organizes things, kind of gives you an idea of maybe where to start and what might be easy to sort of balance. Uh, Two things that you need to make sure when you are all said and done in terms of balancing the equation is all the coefficients need to be whole numbers, the coefficients, and they need to be the simplest set of whole numbers. So again, what can happen is maybe some people may see sort of larger numbers to use to balance the equation, and it may definitely be balanced. You may have the same number of elements on each side, but you can still reduce down all those coefficients by a common number and hit whole numbers, and you should do that. So again, if you look at your coefficients at the end and you can kind of divide through all the coefficients by a common number and still get a whole number, you should do that to have a properly balanced equation. And again, sometimes you could have a balance, but again, they're just not the simple set of whole numbers. So we did a number of examples, and I don't remember, did we do this one in here or not? All right, now let's do this one. That seems like a good one. Let's do that one. Okay, so let's take a look. Again, I'm gonna make a little table here. Reactant side, product side. Gonna list my elements: nitrogen, hydrogen, and oxygen. On the left-hand side, we got one nitrogen. Right-hand side, we got one nitrogen. Left-hand side, we have three hydrogens. Right-hand side here, we have two hydrogens. Left-hand side, two oxygens. And right-hand side, we have one oxygen there, plus one more there, gives us two. So in this particular case, everything is balanced except for obviously the hydrogen. Seems like a good place to start. In this case, we actually are going to need to kind of put a number on both sides here to start. So we got 3 on one side, 2 on the other. Common number there is 6 if we just multiply them together, right? So to get my hydrogens on the left-hand side to 6, I would need a 2 there. And to get my hydrogens on the right here to 6, I would need a 3 there. Remember, as we talked about, the coefficient goes for everybody behind in this case, right? So when we start adding it up here, we have 2 nitrogens. We have 3 times 2, which is 6 hydrogens, and 2 oxygens on the left. On the right, we still have 1 nitrogen. 3 times 2 is 6 hydrogens. Now, in terms of oxygen, we have 1 here, and we have 3 times 1 is 3. So that's a grand total of 4 that we got going on at that point. The next really easiest thing to sort of fix is going to be the nitrogen. We can fix the nitrogen by putting a 2 on the right-hand side. And again, this 2 is going to go for everybody behind it. And that means that we have 2 nitrogens, still 6 hydrogens. And now in terms of oxygen, we have 2 here in the first one, and we still have our 3 in our last one here. So that is 5 at that point, All right, so at this point, right, we need to kind of fix the oxygen, and we clearly only have one place left to go, which is the O2 on the left-hand side, and we need to turn basically our 2 into a 5 in this case. So clearly in this case, this would be a case where you could use a fraction to do that. So for example, if I use something like 5/2, that would give me 2 nitrogens, 6 hydrogens, and when I take 5/2 and times it by 2, the 2's cancel and give me 5 oxygens in this case. Can I leave it like that though? I cannot, right? So this is a good example that you can use a fraction to balance an equation, but you cannot leave the fraction. Remember, as we talked about, all the coefficients has to be whole numbers. So in this case, bless you, what we would want to do is clear the fraction by multiplying everybody by, I think they call that the denominator on the bottom there. So we're going to go with 4NH3 That'll give us 5O2, 4NO, and 6. It's like 12, but not H2O in this case. Now, if I did everything correctly here, it should still be balanced. So if we look, we now have 4 nitrogen on the left to match the 4 on the right. We have 4 times 3, which is 12 hydrogens on the left. 6 times 2 is 12 on the right. And oxygen, 5 times 2 is 10. On the right-hand side, we have 4 oxygens there and 6 more there. Give us 10, so we are balanced in this case. So you definitely can use a fraction to balance an equation. And it oftentimes happens in a situation like this where you have kind of a diatomic molecule that's an element on one side, and you got that element in multiple places on the other side. So sometimes a fraction is needed. If you're not sure sort of how to choose your fraction, it's a pretty simple formula. The number on top is the number you need. So if you remember, we needed 5. And the number on the bottom should match the subscript. So it cancels out, which in most cases would probably be a 2. These two guys should match, right? So you're always going to choose the right fraction in that case, yeah. Any questions on that there? Let's take a look. So a couple of things about the first two here. When you do have an equation that has some polyatomic ions in it, for example, here we have sulfate, which might be good for the exam later, just in case you're not familiar. That is calcium sulfate there, by the way, iron 3 sulfate. We want a lot of times it's easier to keep those polyatomic ions together rather than going element by element because there's a lot of sort of multiplying in and everything. You can't go element by element, but again, there's a lot of sort of you have parentheses a lot of times and sort of distributing numbers. So that's the approach I would recommend taking when you can see polyatomic ions on both sides of the equation. Just kind of keep them together, balance them as whole units. So how you would do that in this case, the only polyatomic ion we have is sulfate, so that's where I would start. And that's not one approach where it said start with the most complicated. This is really what it's talking about when you have sort of polyatomic ions. So on the left-hand side, I have 3 sulfates. Right-hand side, I have only 1. So I could fix that really easily by putting a 3 in front of the sulfate. Now, when you do this method, what you want to go next is whatever is attached to sulfate in this case, which is calcium. So by putting the 3 there for the sulfate, it then makes my calcium be 3. So that's where you should go next to fix the calcium. And when I do the calcium, that then goes to the chlorine, which is where I should go next. And now I have 6 chlorines on the left, which means to fix it over here, I need 2 for my chlorine. Also gives me the 2 that I need for my iron. So that's a lot easier way to balance equations that have polyatomic ions in it, is to keep them together. Start with those. Once you balance the first polyatomic ion, then go to whatever it's attached to and kind of go back and forth. Eventually, everything will sort of fall into place. And again, it's sometimes a lot easier and a lot faster than kind of going element by element, especially with those polyatomic ions. Any questions on that there? Now, we could do kind of the same approach on the next one. We have nitrate on both sides, right? And we have phosphate on both sides, right? And you could really start with either one. In some cases, it may be okay no matter which one you start with. Some cases, it may not work out great for you. So for example, if I started with the nitrate and I put a 2 over here to fix my nitrate, that means I should go to my copper next. And that's a problem because my copper has 3 and I only have 2 on this side. So maybe that's not the best one to start with in this case. You could actually fix it pretty easily by just multiplying those 2 numbers together, and it'll tell you the number you actually need. But if that happens, you just erase it. That's why they kind of invented erasers, I suppose. And then you blank the screen, and then you turn the screen back on. And then you start with the other one. So in this case, I'm going to start with phosphate. I have 1 phosphate on the left and 2 on the right. So I'm going to do a 2 for my phosphate. Now I'm going to go to my copper next, which is 6. And that 6 for the copper means I need 6 nitrates. And I'll put my 3 over here, and that gives me the 3 bariums that I need. And now I'm balanced, really quickly. So as I mentioned before, even though I started with the nitrate and kind of didn't work out, I had a 2 that I put there for the nitrate, and it had a 3 for the copper on the other side. So if I took 3 times 2 is 6 is really the number that I needed over there. So you could kind of adjust midway if you needed to go that way as well. Any question on those 2? All right, let's take a look at the last one here. I think I'm gonna flip the page, rewrite it. A little C4H10, a little O2, and some CO2 and some water. This one I don't have polyatomic ions, so I am going to go back to sort of the table method here, and I'm going to write it in the right order, put that in R and that a P. That's a long night. All right, let's try that again. There we go. All right, we got carbon, hydrogens, and oxygens going on. We got 4 carbons on the left, 1 on the right, 10 hydrogens on the left, 2 on the right, 2 oxygens, and once again, we have 3 oxygens there on the right-hand side. So the easiest thing really to fix here is just the carbon, since it's on one side, one thing in each side. We could put a 4 in front of it. That again is going to go for everybody behind it. So that's going to give me 4 carbons, still 2 hydrogens. Now in terms of the oxygen, I have 8 happening there and 1 there, which would give me 9 in this case. At this point, like we talked about, I think last time, I'm actually going to go with the hydrogen here since oxygen's in a lot of places there in both sides of the equation. We could fix the hydrogen really easily by putting a 5 there. Once again, that's going to go for everybody behind. So that's going to give me 4 carbons, 10 hydrogens. And now in terms of the oxygen, I still have 8 on the first one, and now I have 5 there on the second one. And that is a 13, I think. So in this case, once again, we really don't want to play with any of the other numbers as they are sort of locked into place. So this is a good place where we can kind of turn our 2 into a 13, and a fraction is a good way to do that. Once again, the number on top is the number we need. So we need 13. So that is what goes on top. The number on the bottom should match this guy so that they all cancel out correctly. And that would get us 4 carbons, 10 hydrogens, and 13 over 2 times 2 will give us 13. Any questions on that so far? Now, as we talked about, we can't leave it like that, so we're going to clear the fraction by multiplying everybody by the 2, which is the denominator there in our fraction, and that will give us 2C4H10 plus 13O2 gets us 8 CO2 plus 10 H2O. And again, we should still be balanced. We got now 8 carbons on the left, match the 8 on the right. Hydrogen, we have 20 on the left and 20 on the right, and oxygen's 26 on each side, 16 here and 10 there. Going to give us 26. Yeah. Any questions on how to balance equations? So polyatomic ions, keep them together, balance them as units. Everybody else make a table probably and go again element by element what's easiest to balance and kind of save the more complicated guy for the end. Any questions? All right, that wraps up chapter 6.